Fluid dynamics is when fluid flows inside a tube. Suppose this is a tube and fluid flows inside the tube, right? Fluid flows inside the tube. Now this flow may be of different types.
Number 1, I guess so.
Okay, no problem. You just send me that question in my WhatsApp. I will check.
Okay, sir.
So in a tube or in a pipe, if fluid is flowing, then this is called fluid dynamics. Now there are two types of fluid flow that we can observe in our daily life also. Suppose you have a, you can see that if there is a tap, right? If there is a tap and if water is coming from the tap, you will see that if the speed of the water is small, it is not very large, speed of the water, it is slow, then you will find that the water is coming down the tap.
Yes, sir. Yes, sir.
Like this. And this water is coming very smoothly, right? Smoothly means
Yes, sir.
the water is not going here and there. But as soon as you increase the speed, you will find that through the same tap, the water is now moving here and there.
Sir, I couldn't observe that one. Means it's going here and there.
So, sir, I am saying, yes, sir, it comes. So when I do it in very small speed, I see a spiral type of thing is formed.
Spiral? Why
It means
spiral?
some flow of water was to go over the other, and in that way they just rounded up.
It
Yes, it
may
looks
be
like that.
due to this cross section. It may be due to the cross section of this wire net. They may be.
No such net.
Sir, they get attracted towards each other. That
Yes,
might
sir.
be the.
No, that is not. Attraction force is there definitely, but it is not due to this. So there are two types of water flow you can see. If you see in a river where the water current is less, water current is not that high, you will find that water is flowing very smoothly. Whereas if you see in a mountain river where water current is very high, you will find that the water is forming ripples and water
Yes,
is
sir,
moving
yes,
here
sir.
and there, right? So these two types of flows are there, and these two types of flows are known as, one is known as steady flow,
Turbulent.
steady flow, another is turbulent flow, right? Steady and turbulent, by the name only you can understand. Steady means this shape of this water will not change. If the speed remains same, you will not find any change in the shape of this water column. But here the water column is not only this one. After some time you will find this water maybe some flowing in some other
Something
way,
else. Some other trajectory.
right? So turbulent flow, there is no fixed shape, no fixed shape, right? And steady flow, the water is flowing in a fixed shape, right? Basically we will talk about steady flow throughout our study because it can be analyzed. You can discuss with steady flow. Turbulent flow, if there is no fixed shape, then how you can discuss the water flow, right? Or fluid flow, we cannot discuss it. So we will not take this into account. We'll only study steady flow, will not study turbulent flow, right? Before understanding that steady flow and turbulent flow bit details, this is fluid dynamics in details, let us try to understand two basic definitions that is important in this discussion. One is streamline, right? So what is a streamline? Streamlines, as it is written, you can see these are set of imaginary lines connecting all the fluid particles such that tangent at any point on the lines shows the direction of velocity of the fluid particle present at that point at that instant. So it is a lengthy definition, but let me clear you what is.
Can you please say once more the definition?
Yes, I will now try to make you clear with a diagram. Also, I will send you one video regarding this. It is an animated video. You will see all these things in animated video very clearly. Right? I will send today only. So suppose this is a tube and fluid is flowing inside that tube, right? So if you see that, if I say that there are suppose few fluid particles, right? I have marked them. One fluid particle is yellow, one is white, one fluid particle is red, right? Let me mark different fluid particles like this.
Sir, I have just one color.
No problem. Particle 1, 2, 3, 4, you name it. A, B, C, D, you name it. Okay. So suppose there are, let us name them, 4 fluid particles that I have drawn here, right? And what you have done, you have noticed that at this particular instant, this fluid particle is moving in this direction. Velocity of this fluid particle is in this direction. Right? Velocity of this fluid particle is in this direction. Velocity of this fluid particle is in this direction, and velocity of this fluid particle is in this direction. At this particular instant, these velocities are noted, the directions. Now you want to join all the fluid particles with a set of lines, imaginary lines definitely. But you cannot join them with any arbitrary line. Suppose you want to join the fluid particles like this. You want to join the fluid particles like this. Like this. So you cannot say this is a streamline. Although I have joined 1, 2, 4, these 3 particles with that streamline, but I cannot say it is a streamline. Why? Because you can see point 1, if this is a streamline, the tangent at this point should be along this line. The property of streamline should be that if you draw tangent at any point on the streamline, you should find the direction of velocity of the fluid particle present. Can I draw a tangent at this point and I will not find the tangent in this direction? Yes or no?
You will not find, sir.
Yes, sir.
At this point also I will not find tangent in this direction. So this line does not qualify to be a streamline.
Sir, then why did we draw it?
Which one?
To explain.
That streamline. I'm saying that
Line.
streamline, this line is not a streamline. To explain that this line is not a streamline. So what is the property of streamline? Now I will draw a streamline and you will see that this line will represent a streamline. How we will draw? Suppose
We'll draw such that the tangents are along that.
yes. Suppose now I draw the streamline like this. You can see I have drawn the points 1 and 3. I have joined point 1 and 3 with that streamline. I can also join points 1 and 4 with another streamline like this.
The 2 and 4.
And 2 and 4.
2 and 4. You can see now this streamline, as I have drawn, 1 and 3 lie on that streamline, and also I can say that the point, if I draw tangent at this point 1, I will find the direction of fluid velocity at this point. If I draw tangent at this point 3, I can find a direction of fluid velocity at this point. Yes or no?
Yes, sir.
Yes, sir.
Similar is the case for 2 and 4. So these two lines qualify for being streamlines. Right? So what are streamlines? Now you can say the definition that streamlines are set of imaginary lines, not one streamline. One particular streamlines cannot join all the fluid particles. Right? To join all the fluid particles, you want set of streamlines. So this may be another set of streamline. This may be another streamline. Right?
So I have drawn a curvy streamline. Will that work?
That you have to understand. There are another property of streamline, that no two streamlines ever cross each other.
So just like magnetic field lines, we let Rasti here.
Yes.
No two field lines will cross each other. The reason is very simple. Can anyone tell me why I'll say that no two?
The velocity will not be determinable.
Yes.
At
Sir,
that
Velocity-
at
the
that
point
point
of
where the line
intersection.
intersects, velocity
yes.
direction cannot be 2.
Good. At the point of intersection, you will find two different directions or the two different tangents. That is not possible at a particular point. The velocity are not two different ways. So I can say that streamline has a important properties. One property is that every point, if I draw tangent, I will find the velocity at that point. And the second one is that they do not intersect each other. Have you got about this idea of streamlines?
So please wait a bit. Yes, sir. Done.
Done? Okay. This is streamline. Now, so can I only define streamline in case of a steady flow, or I can also say that streamlines are there also in case of turbulent flow?
So
Sir,
only steady, because in turbulent,
only
anything can be
steady flow.
possible in any direction.
Look, turbulent flow also has
sir.
streamlines. Streamlines are not only defined for a steady flow, but you have to understand the difference. In streamline,
Sir, I have a question, sir.
Yes, yes.
Yes. So this streamline, is for a particular time, means that I couldn't get.
Yes, yes. Now I will come to the part time. Look,
Which
if it is a steady flow, you will find that the shape of the streamlines are always in this way. Yes or no?
Yes.
Yes, sir.
But if it is a turbulent flow, you will find the shape of the streamlines at t equal to 0 maybe like this, and shape of the streamline at t equal to some other point maybe like this at other time.
Okay, sir.
Some other time the shape of the streamlines may be like this.
Oh, sir, nice.
Right? So these all are turbulent flow. Now you should understand how I can differentiate a steady flow and turbulent flow by the definition of streamline.
So this turbulent, this part, can you repeat one? The time one.
Yes, I have said that in steady flow, if you suppose keep looking on this shape of the streamlines, you will find that they are flowing in the same path. As I mentioned in earlier the slide, that the shape of the steady flow is fixed. Do you remember that? But
Yes,
in
sir.
turbulent flow, the shapes are kept on changing continuously. So if at t equal to 0, t equal to t1, the shape is like this. T equal to t2, the shape should be like this. T equal to t3, the shape may be anything. You
At the
cannot
same
predict.
location only it will change the shape.
Yes?
At the same location only the shapes will change.
Yes. At the same point, the shapes will change. It depends on time. And also, it may not be a function of time. So it may be unpredictable. Right? It's not that it will change in a particular way. Right? It may be unpredictable. But
Yes,
in
sir.
steady flow, it is
So why
always,
is it so?
because of the nature of this fluid flow. Right? We can now say why it is so. That also has internal reason. Now we can understand one thing. Very important thing is that if you go into this definition of steady flow, we have seen that steady flow, if I suppose this is a streamline, right? This is a streamline. This is a particular streamline. We have drawn that streamline in xy coordinate. Suppose this is a two-dimensional streamline, xy coordinate. At this particular point, what is the direction of velocity? Can I say this will be the direction of velocity only?
Yes, sir.
And if you see that the direction of velocity, I can also find this tan theta by y by vx.
Yes, sir.
Yes, sir.
Right? I'm talking about a particular point x comma y. So can I say at that particular point tan theta is nothing but the slope also?
Yes, sir.
Sir, can you please repeat this theta part?
This is theta and this is also theta. Na? This is, I have drawn a tangent.
And that is the direction of velocity, and you are finding the inclination of velocity.
And direction of velocity is nothing but the tangent at this point.
Yes, the slope.
Slope, yes. right? So I can say that slope is equal to tan theta, and which is equal to Vy by Vx. And can I also say that slope is nothing but dy by dx?
Yes,
Yes,
sir.
sir.
We can say that.
Can
I write this? Check once.
Please wait a bit, please.
Yes, sir. We can write this.
Vy dx is equal to Vy Vx.
For any streamline, we can do it.
Yes, sir.
Right?
Yes, sir.
Now
Okay,
listen.
so this is a mathematical manifestation of streamline.
Yes, definitely. Now listen to carefully. If I say that Vy and Vx does not change with time, Vy and Vx does not change with time, can I say that the shape of the streamline will not change with time?
Yes, sir. We can say that.
If Vx and Vy are in terms of V, if I say if V does not change with time, does
The
not
velocity is
change
constant.
with time, then dy by dx does not change with time, is constant with time.
Yes, sir.
So what type of motion is that? Steady flow or
Magnitude of
turbulent
V
flow? then?
changes.
Yes, steady flow. Now
If
can
magnitude of V changes,
if what changes?
the
Then also it will
magnitude of
change.
V
Okay,
changes.
V vector is not changing. How can magnitude
V
change?
vector does not change. Actually, I am saying V vector does not change. Neither its magnitude nor its direction. Nothing is changing.
So I'm saying one thing that Vy Vx, you have proved from direction thing. If a slope thing, you have proved that V dash means V vector does not change. How can you conclude that from direction thing means Vy can be double, Vx can
I am
also
not
become double.
concluding from here.
So how about that?
I am not concluding from here. I am saying that if V vector does not change with time, can I say that the slope is a constant? I am not saying reverse thing.
Yes, slope is a constant.
I am not saying if the slope is a constant, then V vector is the constant. That is not a correct statement. I am saying that if
Yes,
V
sir.
vector is not changing, can I say slope is constant?
Yes, sir. Yes, sir.
Yes,
That
sir.
is the
Okay.
steady flow. You may
Sir,
say
means
that
slope is constant means that velocity's direction means everything is path is constant, so it's
that
steady.
path is constant. So in steady flow, is that statement correct? That in steady flow, the dy by dx is constant everywhere.
No, not everywhere. Not everywhere.
Then what should be the correct statement?
So at a point with
Yes.
time, dy by dx is
At a
constant.
particular point, dy by dx is constant. If you move to this point, will you find the same dy by dx?
Never, sir.
No. But whatever you find that dy by dx, that will remain constant with time.
At that point.
Yes, at that point.
Means it will remain constant everywhere.
It will remain constant with respect to time, but not with respect to position. Dy by
Yes.
dx.
Not everywhere.
Yes. So velocity in steady flow is a function of position, not a function of time. Can you understand that?
So please wait. Velocity. Yes, sir.
Yes.
Yes, sir. Yes, sir. It's interesting.
Velocity of steady flow, suppose this velocity v vector, if it is a steady flow, you have to say that this velocity is constant with respect to time, not with respect to position, because this velocity, if it is v2, you cannot say this velocity is also v1. This velocity has to be v1. These are different. Can you see
Means the
that?
velocity at a point is position dependent. Means at this point it will be in this
Yes.
direction.
Yes. And more interestingly, suppose it is position dependent, not particle dependent also. Suppose this yellow color particle after some time comes to the position 3, then what can I say about the velocity of this yellow color particle?
It will become v2.
V
It will become v2. Have you got it?
Yes, sir.
Yes, sir.
This white color particle after some time will come here. So can I say what is the velocity of this white color particle when it will come here?
V4.
V4. Right? So in steady flow, you can actually determine what is the velocity of any fluid particle that is passing through a particular point if you know what is the velocity of this point at any instant.
Yes, sir.
But turbulent flow, it's completely opposite to that. Turbulent flow, you cannot predict what is the velocity because it will be a function of time. Even if sometimes you will not find a particular function of velocity with time. Right?
Yes, sir. It may be anything, sir. It may be
Anything.
random also.
Yeah. So that is why turbulent flow we do not study. We will only study steady flow. And in steady flow, the properties are very clear to you. Steady flow means the streamline shape will never change. Steady flow means the streamline shape will never change. At a particular point, the slope remains constant or the width does not change with respect to time. Right? But different points may have different velocities.
Sir, I have a question.
Yes.
Yes, sir. So I am saying that in a streamline,
Mhm.
so suppose I have drawn a curve, and at 2 points, suppose the velocities of particles are same in magnitude and direction. It may happen.
It may happen, mostly in this case of, yes, it may happen. It may happen.
Yes. Suppose you draw something like a sine curve, then you will find that it means means many points you will find the same velocity in magnitude and direction.
Yes, yes.
Then
yes.
what to say about that?
No, that may be possible. Suppose this point and this point may have the same velocity in magnitude and direction.
Yes, that I'm saying.
Right? Yes. So that is also a part of streamline, steady flow. I'm not saying that all the points must be different. They may be different. It's not that all the point velocity must be different.
Position dependent means at that position velocity will be same.
Yes, at that position the velocity is v only.
Okay, sir. Okay, sir.
Have you got a clear idea? Look, you will not find in any book this discussion, right? You will definitely study in when you will study in higher classes, you will get to know more about that streamline or path line. What many different lines are defined, but only streamline is important for our discussion. But it is important to understand when you talk about steady flow that the streamlines, if you can draw any streamline you can draw, right? If it is not mentioned, you can draw streamlines anyway, but you have to take care that the velocity should be the tangent of that point at any point on the streamlines and they do not cross each other, right?
Voice is stopping at a certain instant. This turbulent voice.
All right, my internet connection may be unstable. Can you hear me now?
So it means stopping means like speed breaker. It is stopping something.
Yes, sir.
Yes, due to poor internet connection, what we can do. Oh, all right. Okay, up to this, is there any doubt you can ask me?
Please wait, I'm writing.
Yes.
Please wait for a minute.
Yes, sir. Done.
Done? Okay. Alright, so after we have studied what is streamline and steady flow, now we will move to the equation of continuity. Right? What is
Sir,
equation?
please go to the streamline page once. Sir, what was the second definition? Yes, flow is steady velocity of fluid particles at a position. Okay, sir.
Right? At a position does not change with time. Okay. Equation of continuity is a very basic thing. There is not much physics in this equation of continuity. It says that suppose there is a tube of arbitrary cross section, different variable cross section, right? Where the cross section area here is A1. Suppose this cross section area is A1 and this cross section area is A2. Right? And a liquid is there which is flowing inside this tube. Now, if I say that there is one part of the liquid that is entering this pipe, if suppose this liquid is entering this part with a velocity v1 and the same liquid is leaving this part with a velocity v2, can I say that as the liquid is incompressible, this much part volume of the liquid, if it is going inside, the same volume of the liquid should come outside of the tube?
True, sir. True.
In a given time.
In a given time. So I can say that in a given time delta t, why I have taken small delta t, small time delta t? Because in that time I can assume that these velocities, these particles have not changed their position much, so that the velocities are almost remaining the same.
Sir, also diameter constant.
Yes, also the area, you can say area is constant. So everything is constant inside this delta t. So I can say that the volume of the liquid that is entering is A1 V1 delta t.
Yes, sir.
Because this length is V1 delta t or not?
Yes, sir, the volume.
Similarly, the volume that is coming out, this is V2 delta t. So that volume is A2 V2 delta t.
Yes, sir.
So can I say that A1 V1 is equal to A2 V2?
Yes, sir, we can say that.
This is the equation.
That is the equation of continuity. Right? This is the equation of continuity. As I have told you that there is no physics here. There is only, we can conserve the volume.
মানে যতটা ভিতরে ঢুকছে ততটা মানে বাইরে
ততটাই
আসছে
liquid বেরিয়ে যাবে. Now this part, this A1 and V1, A into V, this is also known as volume flow rate.
volume flux.
Yes, volume flow rate, generally denoted as Q. Right? Volume flow rate means volume per second, meter cube per second. This much of fluid is flowing through the tube per second. It is constant throughout. Even if you take any arbitrary cross section, can you see that in this cross section also the volume flow rate is Q?
Yes, sir. It has to be.
Yes. So everyone, A1, V1.
Volume flow rate means volume.
Flow rate means volume flow rate. Rate means per second. Per second, how much volume is flowing?
Okay.
Through any cross section.
Yes, sir.
All right. So this is equation of continuity. Now,
The wait.
Yes.
Yes, sir, done.
Now come to this Bernoulli's equation, right? So this is the important equation. Based on this equation, we will continue the last portion of this chapter. Right. The rest of the part of this chapter is only based on this Bernoulli's equation. What is this Bernoulli equation? Let us try to understand. Bernoulli equation can be proved in two different ways. Let us first try to understand it in a very conventional way, which is conservation of energy. Suppose we have a fluid flowing in a tube like this. The tube is having a varying cross section. Also, the vertical height of these two cross sections are different from ground. If you see, this is the ground level. This height may be h1 and this height may be h2. Right? So, suppose the liquid is flowing inside it. If I say in a time delta t, this part liquid is entering the tube. How much part of the liquid is entering the tube in this time delta t?
It's A1 into V1 into delta T.
Yes. This distance is V1 delta t. Similarly, the same volume liquid is going out of the tube in the same time interval. Let us assume that pressure here is P1, pressure there is P2. It may happen that both the pressures are atmospheric pressure, so P1 and P2 are same.
So this pressure is of what? Means that I cannot get once.
Look,
Means-
pressure at a particular point is always same. If you see pressure at this point is P1, pressure of this point is also P1. It may be due
So
to
means
this
pressure at
liquid.
cross section you can say.
Yes, at this cross section. It may be from this side, if you come, it may be due to this liquid. From this side, it may be due to the atmosphere. Pressure at one point may be found in different conditions, but one point pressure is always same.
Okay, sir. Okay, sir.
So I will see this situation in that way. Can you see that during this delta t time, this much fluid has gone inside the tube and this much as fluid has come out of the tube?
True, sir, true.
Can I say that in this time, if I consider that inside fluid is not changing their position, although it is not true, inside all the fluids are actually shifting their positions a bit, right?
Yes.
But
What are
I
you
can
saying?
say for my calculation purpose that inside fluid has not shifted their position. I have only shifted this entire chunk of fluid from here to here.
Yes, we can imagine.
Yes, there is no deviation of this conservation of energy principle if we imagine this situation and from the initial original situation. There is no deviation from these two situations. Yes or no?
Yes, sir. No deviation as such.
True, sir, true.
Yes. So this is my initial position 1 and this is my final position 2. I will conserve energy. Now tell me what is the final energy 2 minus 1. Energy, conservation of energy, you remember? Total energy 2 minus total energy 1 is equal to work done by external force. It was the energy principle, I think.
Work done by non-conservative.
Yes, all the other forces here we can assume.
Other forces.
Now energy at 2 position, can I say this energy is equal to mass m2 g into h2,
Absolutely.
right? Plus kinetic energy is half m2 v2 square. Yes or no? Minus E1 is M1 GH1 minus half M1 V1 square. Look, what is external force here? Can you tell me? What is the work done by external force?
So external force is here weight.
Not weight. Weight I have taken mgh. Weight means the gravitational force.
Pressure into area.
Pressure into
Yes,
Difference of
this
pressure into
force.
area.
If the liquid is pushing inside, then there is a force on this part of the liquid. You can see if this is my liquid, there is a force from this side, which is P1 into A1. And there is a force from this side, which is P2 into A2.
Sir, but there is also gravitational force, isn't it?
Gravitational
Not
force, I
not
have
non-conservative.
already taken gravitational effect inside the energy.
Sir, I have a question.
Yes.
Okay, sir. Okay, sir. Okay,
The
sir.
P2A2 is exerting force in which direction?
Always, what is the force? Force is compressive in nature or not? Pressure force?
Okay, sir, got it.
It is
Got it, sir.
compressive nature, so that should also be compressive in nature.
Hmm.
Can I say this work done is P1 A1 V1 delta T minus P2 A2 V2 delta T?
Minus.
Because this volume is coming out in this direction. V2 delta T
Yes,
is in this
sir.
direction. And this force is in opposite direction. And here that force is in the same direction as that of V2 delta V1 delta T.
Please wait a bit. P2A2. So means one side it's in opposite direction. So
Yes, this P2 A2 is in opposite direction that of the displacement.
okay, sir.
Alright, now we can say M1 is equal to M2 is equal to rho A1 V1 is equal to rho A2 V2. Can I say that? All these things are same or not?
Rho A1
Delta T.
V.
Sir, I get confused. I got.
Where?
Oh my goodness.
Where?
Oh, okay, sir. Okay, sir. I get it.
Yes,
A1
sir.
V1 equal to A2 VT. Multiply it with delta T and then multiply it with rho. You will find M1 and M2.
Yes, sir, got it.
Got it? So look, rho A1 V1 delta T, can I replace it with M1 by rho and this is M2 by rho?
M1 by rho.
Yes. A1 V1 delta T, A1 V1 delta T.
Sir, I got locked out. আপনি ওখানে কি লিখেছেন M1 is equal to M2?
This mass that is going inside and coming outside, both are mass the same or not?
Yes, sir.
So that is equal to rho into A1 V1 delta T from here and rho into A2 V2 delta
Yes,
T
sir,
from
got
this
it.
side. They are all same. Now let me write the same equation in this form. Rho, it's not there. It's A1 V1 delta T. I can say it is M1 by rho. So M1 P1 by rho minus M2 P2 by rho.
Okay, sir.
Now I can cancel M1, M2, all of them.
It's all the same thing you are saying.
Yes. So if I take these things in one side, right?
Sir, at first you write one step, sir, please.
Which one step?
So miss
From here to here, have you got it? I have just kept
yes.
A1 V1 delta T as M1 by rho, A2 V2 delta T by M2 by rho.
Okay, sir.
Sir.
Got it.
Bolo?
Sir, in LHS you have written what? Plus or minus? RHS, sorry, RHS.
Minus, that is minus.
Yes, sir. So now you can write that P1 plus half rho
P1
V1 square
plus half, if I multiply it with rho, P1 plus half rho V1 square plus rho GH1, is it equal to P2 plus half rho V2 square plus rho GH2?
Yes, sir, it has to be.
Right? Out of that, P plus rho GH, we have studied that it is a pressure. Hydrostatic pressure also we have seen that it is P plus rho GH. We have also seen that in hydrostatic part. But what is this part? Is it also a pressure?
Yes, sir, it is by virtue of the motion.
It is, yes. This pressure is known as dynamic pressure.
Sir, I couldn't get this thing, sir.
Look, all the dimensions are of pressure or not?
Yes, sir.
Here, because you
True,
are
sir, true.
adding, so out of that P1 and rho GH1, these are already we have studied in static, hydrostatic also.
Yes.
Yes, sir.
But this pressure have we seen earlier in hydrostatic
No, sir.
part?
No, sir, no, sir.
But that is also a pressure.
So this is where the difference lie between static and this
Yes.
continuity.
This pressure is known as dynamic pressure, right? This pressure is known
And
as
this equation is Bernoulli's equation.
So what is Bernoulli's equation? P plus half rho V square plus rho GH is equal to
Constant.
That is Bernoulli's equation. You need to remember this one.
So please wait a bit. So this P plus rho GH plus half rho V square, this whole term means these three terms collective any name is there.
Total pressure. They say it is a total pressure. Which includes, look, pressure at a particular point. If they ask you what is the pressure, actually they are asking about this P only.
Yes, you have taken to just P1 and P2.
Yes, P is the pressure. But sometimes it says that what is the total pressure. Total pressure means all of them you can understand. But if I only
All these
ask
other
you,
things are also pressure only.
other things are also pressure. Yes, also the dimensions all of them are pressure.
Okay,
Right.
sir.
So actually, if I ask you what is the pressure of the atmosphere here or the outside pressure, then this
It's
pressure
P1 and
is
P2.
only P1 and P2. So pressure, if I ask you, only you have to find the pressure as P1 and P2. These terms, they are coming not due to pressure. You can understand these terms are coming due to energy, mgh and half mv square.
Yes, sir.
Right? So basically, these two terms are correctly said as energy density. If you see, these two terms are energy density.
Energy per unit volume. Yes, sir.
Yes, energy density. Right? And
It's
actually,
total.
this is the pressure. Right? But basically, Bernoulli's equation are used not to measure pressure. Bernoulli's equations are used to measure velocities. That is why this equation are used, right? So pressure, no one is going to ask you the pressure. But even if I ask you what is the pressure, then I will understand this P only. You are asking me about P.
Okay. Miss total pressure also, if you ask, I will say P only.
No, the total pressure, if they mention what is total pressure, then the exam setter is probably asking you to find this total term, which is a constant.
Okay, sir.
Have you got this derivation of
Yes, sir.
There is
Bernoulli?
another proof of this.
Yes?
There is another proof of this.
Yes. Why I will do that proof? That is a bit not complicated proof, but very simple proof that also. But we will not do energy conservation, but we will use Newton's second law of equation, F equal to m into a. Right? Force equation we will apply. Why I will do that? In order to understand the limitations of Bernoulli's equation that no book actually talks about, and that is why in few books they have also used that equation in a wrong way. So that is why to understand it in a deep way, I will try to prove it in a different way by using laws of motion equation. Have you understood this part? Try to understand what I am doing now, right? Not complicated, but again if you feel that it is a bit complicated, go for that proof, but try to understand the limitations what we are doing. The same tube I have drawn. Now let us see that this is one streamline. The fluid is flowing. I am interested in free body diagram of this fluid. Any fluid particle here.
Fluid element.
Yes, any fluid particle I have. Yes, fluid element. I am interested in free body diagram of this fluid element. What is the coordinate of this fluid element? In order to understand the coordinate, let us assume that this height is h. This height is h. Right? And the coordinate, to understand coordinate, I will take one coordinate system here only along this line. This is my coordinate system. This is my x-axis and it is my y-axis. I will try to redraw this fluid element here by taking x and y axis like this. Okay, let us draw it as it is. Okay. Suppose this particle is present here. This is a cuboid particle. Element is cuboidal, right? Let us take the shape of the element as cuboid.
So you have taken the particle at the origin, no?
You can take it at origin or you can take it any.
You have taken it any other position.
Yes, take it any other position, no problem. Not mandatorily it is at origin. Now let us assume that this particle is at a distance x. This particle is at a distance x, right? And this distance is delta x. Okay, and let us assume that at this point the slope is theta. And the area of this surface is.
Which point slope is theta?
At this point, if you draw tangent, this x-axis, it makes angle theta.
With the horizontal, yes,
with
sir.
Horizontal, it makes angle theta. With horizontal line, yes, definitely with horizontal line. This is horizontal. Now, can you tell me what are the forces acting on this fluid element? Only in this x-axis I am interested because the fluid element has a velocity in which direction?
X-axis only.
Along x-axis, right? So the fluid particle, because this is the tangent to the streamline, so I know that the velocity is along this line. So I have assumed that the velocity is along this line. Acceleration is also along this line, right? It is moving with some velocity v along this line. It may have acceleration along this line also. So I will only draw the forces along this line. Can you tell me what are the forces along this?
The pressure force, P times A.
P times A, okay. So what are the pressures? Are the pressures at these 2 points same of the liquid?
No, sir, or else it wouldn't flow.
Definitely, they are not same. So in fluid flow, I will not take the pressures to be the same, right? They are, it is flowing. So
So the mass is negligible, though.
no,
Okay, sir.
mass is negligible in comparison to something you can neglect, not always.
Okay, sir.
So this force is P of x into A. Can I say that?
Yes, sir.
Obviously, sir.
From this side there is another compressive force.
P of x plus dx times A.
P of x plus delta x into A.
Yes, sir.
Anything else along this line I'm talking about?
So component of weight will be
Yes,
there.
component of weight along this direction. What is that weight?
Mg sin theta.
Sin theta.
Yes, dm. If I say dm into g sin theta.
Yes, sir.
Sir, I am saying that. Sir, that which pressure will be more, px plus dx or px?
That I know. I don't know. In my convention, definitely I have taken px plus a more than px or whatever it may be. That I do not know.
It may be anything.
It may be anything. Can we write a force equation now? Now the free body diagram is over. Force equation. Along x-axis.
Force equation along.
P of x plus del x into A.
Along x-axis, pxa
Px equal
minus
to dmg sin theta plus p of x plus del x times A.
a minus dmg sin theta is equal to dm into a. Can I write this?
Yes, sir.
So please wait. Sin theta equal to dm into A. Yes, sir. Okay.
Now what is dm, by the way?
Sir, it's A times del x times density.
Rho. So if I cancel a in both the sides, I can write px minus px plus delta x is equal to dm. I have taken there, right? Okay, all right. Dm will let it that be that side only. Dmg is equal to a. I have cancelled, so it is rho g into delta x sin theta.
Yes, sir.
That is equal to rho into delta x into a.
So this part I
have done nothing. I have just replaced dm by rho a delta x and cancel.
dm is okay. Rho a delta x have replaced. Okay. Rho. So please wait. Rho a.
A I have cancelled out. So rho delta x I have only written. Rho delta x.
And you cancel out the area also. Okay. Okay, sir. Okay, sir. Got it. Got it.
Everyone got it?
Yes, sir.
Now I can do one thing. Can I say this is, if I multiply it with delta x, suppose divide it with delta x, delta x, delta x, delta x. Can I do it?
Take limits.
Can I do it?
Yes, sir.
Limit delta x tends to 0. What is this one?
Minus of dp dx.
Minus d.
Minus dp dx.
Yes, sir.
Minus rho g sin theta minus rho a is v into dv by dx.
A is v dv dx. Yes, sir.
Can I write it?
Yes, sir. You may.
Yes, sir.
Now I will write it. Negative sign I will cancel. dp plus rho g into dx sin theta plus rho into v dv equal to 0. Can I do it?
Rho v dv equal to 0. Yes, sir.
Sir, I have a doubt in
Yes,
that.
yes. Tell me.
Sir, PV dV by dx, that part.
Rho v dv dx. Acceleration is equal to v dv dx or not?
So x is the small displacement, no?
Yes, x is along this line. Acceleration is equal to v dv dx. Do you remember that formula?
Yes, sir. Yes, sir. In kinematics.
Kinematics, we have done that. If you do
Very good,
not,
sir.
if you do not remember, just check kinematics. We can do it.
Yes, sir.
Now, can you tell me what is dx sine theta?
So
Look,
dx sine theta.
it is dx and this is theta. So is it dx sine theta or delta x sine theta, whatever you can say?
In height.
With height.
Is it dh or not?
Yes, sir, it is DH.
Because height was in this direction.
So dx sine theta is dh. Yes, sir. Yes, sir.
So you can see the formula becomes dp plus rho g dh plus rho v dv is equal to 0. Now if you integrate all the terms,
We'll get everything.
then we'll get p plus rho gh plus half rho v square equal to constant.
Rho gh plus. Yes, sir. Yes,
Which
sir.
is
We are
nothing but
getting.
Bernoulli's
Okay,
equation.
integrated from where the limits?
I have not taken any limit. That is why I have put a constant.
Yes, sir, that's C part.
Yes, that's C.
So please wait. I will. Okay, sir. Okay, sir. Got it.
Got it? Everyone clear?
Yes, sir.
Now try
Yes.
to understand one very important limit. Now you can understand all the limitations, right? First limitation, I can do this integration only when rho is inside the rho is outside the integration. Rho I have taken constant or not?
Yes, sir.
Yes, that's visible.
Rho is constant. I can do it only when rho is constant. The forces, what forces I have taken? Only pressure and weight. Was there any friction force?
No other forces.
No forces other than weight and pressure force.
Yes, sir.
Yes, sir.
Pressure force. Yes, sir.
Yes, all these are limitations, remember. Third limitation, most important, which limitation is not actually that I was saying that every book
Not
they
visible.
do not yes, they do not consider that limitation and they apply Bernoulli's equation. Where I have proved this Bernoulli's equation along this streamline, yes or no?
Oh, sir. Yes, sir.
Sir.
One particular streamline you can apply Bernoulli's equation. Can you apply Bernoulli equation from this point to this point to this point? Any point you can apply. Can you apply Bernoulli's equation?
Along streamline.
No.
No, sir. Only along one.
Yes, along one particular streamline, strictly you can apply Bernoulli's equation.
Sir.
Bolo.
Sir, in means suppose if other point I take means what is the problem?
Okay, I will tell you. We can apply
I'm not getting.
only along a streamline. Look, if you apply Bernoulli's equation between this point and this point, suppose, any other point, there is a vertical displacement also.
Yes, sir.
So whenever there is a vertical displacement, you have to also consider the vertical forces. It is not always true that vertical forces are always balanced. Can you apply Bernoulli's equation along this vertical line?
No, sir.
No, sir, we can't.
No.
So it is applicable only during a time instant then.
No, I have applied Bernoulli's when I have integrated this thing. I have integrated
Along the streamline.
along this streamline every point I can do it. But how I can do it in between two streamlines? Suppose one point is here and another point is here on the other streamline. It may be just above this streamline. How can I apply these 2 points? I can integrate this one. Can I integrate this equation for these two particles?
No, sir.
I can.
Sir, but there means you were saying the forces will be different, so due to difference in levels.
Forces will be different. Yes. Here, this point, if the forces, look, there may be different cases. This for you can take this particle. Suppose I have taken this particle, right? So here I can say that this force is P of x into A. Are you
Yes,
sure
sir.
that this force is P of x plus delta x into A only?
Sir, I am not getting. You have drawn a cuboid.
Yes.
Okay.
I have said that this fluid particle strictly lie on one streamline. If this fluid particle has a particular height, can I say this fluid particle, the pressure at this point is P of x plus delta x, no problem. That I have taken. P plus delta x into A. At this point, you can see P of x plus delta x into A force I have taken.
Yes, I have no problem. Yes.
But if this height is more, suppose these 2 points are lying on two different streamlines, can you tell that this pressure is also P of x plus delta x into A? Because there
No,
is
sir,
also...
It is not only function of position.
Yes, the
It is
pressure,
something else
pressure
also.
may be anything, you do not know. If the pressure is luckily same, your streamline, this equation will work. That is why few questions work.
Okay, sir, but few questions only.
Definitely, you cannot use that equation for all the streamlines. Any points, you cannot do it.
Okay, sir. Understood, sir. Clear.
Understood? So
Yes,
only
sir.
one
Sir,
streamline. Yes.
Sir, I have a doubt in the in that how we cannot get rho inside the integration. Rho can rho's equation
If
can be
rho
given
is
how
a
it varies with
variable,
x, and that way we cannot find.
if rho is a variable, you can integrate it. But will you find this equation?
No, not this equation. Not this equation we can't.
Yes, that is why this equation is more important. If density is varying, you can use this equation.
Oh, so, sir, means that is the equation.
Yes, this is known as differential form of Bernoulli's equation.
So please wait, sir. Yes, sir.
Okay. So these
Yes,
three are
sir.
limitations, and another thing we should understand from this graph, from this derivations only, that look, what is the pressure difference between these 2 points? Can you tell me what is the pressure difference between these 2 points? Vertical.
No pressure difference, I think.
Vertical, there is a pressure difference due to this, because if you apply vertical forces, then there is a weight component of weight. Yes or
No,
no?
sir. No, it is a fluid element.
Yes, yes.
But the height is negligible.
Yes, sir.
But we have taken here the weight in this direction. Why I will neglect cos theta
The
component?
weight you have to take, sir. Weight you have to take.
Yes. Look, if I take the weight component, then the pressure must be different. The pressure is not the same, because the pressure
sir.
difference force will only balance the weight component.
Yes,
or
sir.
no? But so can I say that along the perpendicular to the streamline, the pressure varies as a static pressure, because here there is no component of half rho v square will come.
So please wait.
Please repeat.
But kinetic part is not here.
Yes, kinetic dynamic pressure will be absent. I will write down the
There's no
statement.
velocity associated with that.
Yes.
Sir, please repeat.
I will write this. Along perpendicular to a streamline, no dynamic pressure is there.
Because velocity is not in that way.
Yes.
So this I didn't get.
If you equate the forces here, will there be any function of velocity or net
No,
force
sir.
equal to 0 here? The net force will be equal to 0.
No, sir. How we got velocity then in that?
In this
Means-
way, acceleration was there.
Okay, means no kinetic function will get.
Yes, but there also as a point to understand here, acceleration is 0. Is it always true that in perpendicular direction acceleration is always 0?
No,
No,
sir.
if it moves, then there will be some acceleration.
Yes. When there is an acceleration?
When
It
the
moves in a curve. If it has some radius of
Yes,
curvature.
good. When the streamline is curved. When the streamline is curved, there is a centripetal acceleration. In that case, we cannot do it.
Oh, sir, it's really dangerous. So many things to keep in
So
mind.
many things. These 4 points you have to remember. Okay, I will simplify this fourth point. If the streamlines are straight, if the streamlines are horizontal, then along this line, no half rho v square component will be there.
So we cannot use Bernoulli's equation along that line, you were saying, so.
Yes, we cannot use Bernoulli. It is a simple hydrostatic pressure difference. If the height difference is h, this point is P naught, this point will be P naught plus rho gh.
No, yes, means what is the problem? Means what limitation you were saying? Means
Limitation
we
I am
cannot
saying,
use equation.
yes. If it is not a limitation, it is only a point of Bernoulli's equation, you can say. If this streamlines are curved,
Then there is a net acceleration.
yes, then I cannot use this one. Then there will be a term of half rho v square, but it is not in your syllabus. We will not study that in details.
So that part is not there. So that curvature.
That curved part is not in our syllabus, but you can understand that there will be a dynamic pressure difference also along perpendicular to the streamline.
Due to that centripetal.
Yes.
Okay, sir.
Right, centripetal accelerations will be there. As no acceleration is there. Okay. So that is why I always prefer this particular derivation. So many things you can understand from this particular derivations which you cannot understand from energy conservation principle.
Yes, sir.
Okay, I will suggest you to again go through this derivations again and again, find your understandings. If there is any doubt we can discuss, but before going into the Bernoulli, the questions are very simple, pretty easy questions. You can definitely solve them. Even if you do not understand all these things, you can solve this, but I want you to understand the logic behind all these questions that we will solve, right? Not every point, any point 1 2 3 4 I can take and I can use Bernoulli's equation. No, we will not do that, right? We'll properly
We'll take
use,
according to the rules.
yes, according to rules, whatever is logical we will do that, right? Okay, so today I'm going to end my class here.